who is one of our energy faculty candidates for mechanical engineering. And we don't usually invite candidates who graduated from the lesser tier schools, but Kelly got her.
I guess I'll go then.
Kelly got her BS in mechanical engineering from Caltech, and then got her 2 master's degrees from MIT, one in Earth, Atmospheric, and Planetary Science, and the other in Aeronautics and Astronautics, and then went on to Carnegie Mellon, where she got her PhD in Engineering and Public Policy. So very interesting and well-rounded background there. And she then went to work, as a consultant for several years, and then went back to Carnegie Mellon, where she's now a research scientist. And what else is on the, would you say, the board of?
No, I'm the youngest elected board of directors member of the American Geophysical Union, which is a roughly 70,000 member professional society. Come to our conference every year in San Francisco. We have free beer at about 3:30 every day.
So I was there for the first time this year, and it's that's a conference, about 20,000 people there, and so to be on the board of directors of AGUs, it's a big deal. So, all right, I guess with that, I'll turn it over to you.
Thanks. Great, so today I've been asked to talk a little bit about my research, both what I've been doing, where I plan to go in the next 10 years here at CSU, and then some of the teaching that I might do in conjunction to that. So specifically I work on urban adaptation to reduce climate change and extreme weather risks to electric power. And this is just a pretty image I have that when you first look at it, you're like, oh, it's a water park. Kelly, why did you put this up here? And actually what it is it is a water park in Pittsburgh, Pennsylvania that used to be a lot of problems with the urban heat island effect and climate change synergistically, causing more heat waves. And so the city's been starting to do some things to protect their blackouts and brownouts in their electric power structure by doing things like putting in water parks where people can go play as opposed to turning in their air conditioning. So you see that was a couple steps from the pure problem of the brownouts and blackouts to some of the solutions. And you'll see that as I talk about my research that they are crossing disciplines like that throughout the day. So first I'd like to take a look at this graph. Oh, it played automatically, great. So this is a figure from Oak Ridge National Labs of the carbon dioxide emissions over the last 100 years in Europe, as well as in the US, and Japan, China, India will show up a little bit later. It's roughly 1910 right now, 1920. These red values keep increasing on the bottom. And basically, this is a graph showing us where our greenhouse gas emissions have been over time from fossil fuel use. Okay, so you can see it's just Europe is a troublemaker, and then of course we have the US, and we have our Japan, China area, and this ended in 2000, but if you extended it on to 2010, 2014, 15, you'd see this area in China start to really develop as being the place that is emitting the most greenhouse gas emissions. So this is what we're dealing with our fossil fuel emissions throughout the world. And so what does this actually mean? As a result, this is what warming has been from fossil fuels and other anthropogenic changes. This is a movie from NASA that took a model of the Earth. The blue areas are the areas that are colder than average over the last 130 years. The red areas are the areas that are warmer than average over the last 130 years. So a lot of natural variability, El Nino, other oscillations going on. But as you start to go to the 70s, 90s, 2000s, you start to see that red really come in. So let's play that again real quick. Remember that fossil fuel video that we just saw where it's sort of even and then started to really blow up, especially in China and India and other countries that are developing to be first world nations. And as you see in the 40s, 50s, 60s, here we go in the 70s, and it's starting to get a lot warmer, 80s, 90s, 2000 and 2010. This is what we're seeing with the warmer temperatures over the last 130 years, being really warm over the land masses. So we got the fossil fuels that are being emitted. We got the increasing temperature. What exactly does this mean? So this sort of warming has a lot of issues that occur, but one of them is related to the extreme events that happen. when you have a little bit of change in the mean, you have can have a large change in extreme events. So this is a graph from Munich Re. Munich Re is a reinsurance company, aka an insurance company that insures insurance companies. That's what they do, reinsurance. They're interested in the number of hazards that are occurring and why from a business perspective. They only pay out when these big things like the volcanoes, earthquakes, storms, floods, or fires, droughts happen. And what we're seeing for this here is that over time, the volcanoes and earthquakes, the number of them, after these guys controlled for population and land use changes and satellite differences and stuff, over the last 30 years, those have stayed about the same. But the number of storms, floods, and fires, droughts, and heat waves that are related to climate change, are related to our fossil fuel use, have been increasing over time. Now, just because the number of events increases doesn't necessarily mean stuff, but as you start to then pull out statistics on what we call here our billion-dollar disasters from NOAA, the number of events each year controlled for inflation that have more than $1 billion of death or more than 50 damages, and those are, generally speaking, sort of increasing over time. Now, this is conflating a lot of things, the signal of the fossil fuels all the way through the climate change to the natural hazards, as well as population and land use changes and some other things. So there's clearly a couple of things that are going on that are causing us risks today. So because of this, I researched urban adaptation for the climate, or to reduce climate change and extreme weather risks. And that's what I have been doing in the last 3-4 years. I'm going to talk a little bit about what I have been doing and then where I'm going to go. So the first part is this concept of the hazard. I've looked at a couple different ways of understanding what the hazards are, what the frequency and intensities might be, either now or in the future. And then secondly, what's happening with society? How are people building? Where are they building? How are they choosing to make decisions about certain things? How would they, for instance, in the electric power industry, assume locations for solar power or wind or other renewable energies based on resource information they know now? And then, where my real strength comes in is in these interdependencies between these two systems. There are a lot of effects that go both ways. For instance, suppose you have a hazard of a flood. Pretty classical example of these interdependencies of you have a flood, you have a city decide to build a flood wall to protect themselves from the flood. And because they're protecting themselves from the flood in their area, their edge effects, you guys have all taken fluid mechanics, around the edge of the flood barrier, so places that did not previously get flooded now get flooded. You see this all over the place. Hydroelectric dams is another big one where this happens, and it's very clear, these connections of what people and the hazards interact. Hydroelectric power is great, it provides you electricity and it regulates the flow, but it does flood a lot of the land upstream. So there's all these types of interactions. Now this is a very high-level piece, and of course this requires a lot of different skill sets to be able to solve some of these problems. And so for the risk reduction research, I'm going to tell you about 7 or 8 different skills and methods that I have used either with students or with my colleagues in the last year in either the peer-reviewed publications I had over the summer or that are in peer review now. One of them is this piece on using economics. And I'll talk a little bit more about this piece in a second because it is continuing on in the future. But this is taking a look at energy efficiency in different buildings and understanding what is the cost to do certain things and how many greenhouse gas reductions are emitted. So I have a student working on some of those life cycle analyses, bringing in capital costs and maintenance costs, as well as energy savings or other pieces over time. We then have for specifically some hazards data, things like working with meteorological data. This was a study where we looked at frequency of ice storm changes in the future, and how, but with the interest from the electric power utility of when an ice storm happens, that's usually one of their major blackout, brownout events, is when the ice storms come and destroy all the transmission lines and everything else. So they said, well, how are these things going to change in the future? We took weather sounding data here and did some comparison to climate models to see how those things might change in the future, and used MATLAB to do some of these maps. The next one is something like one of these heat vulnerability indices or social vulnerability indices. Here we combined diabetes and health-related data with census data, with tax property record data on who had air conditioning and who didn't, with, what else? Oh, satellite data on where the vegetation was or wasn't at the ground. Combine these all into a vulnerability index and took a look at if you then knew where the vulnerability index was and where some current methods were, the beige X's on here, to reduce heat problems, where would you put additional locations? And so that involved both using a lot of data sets as well as using GIS and network analyst tools to understand how to spatially optimize things for demand. Another one that's continuing on here is a peer-reviewed paper we had on solar power, solar photovoltaics in Gujarat, India. For the first time that we're aware of, we had collected real-time generation data at roughly minute intervals for 50 power plants in India. And they weren't exactly 1 minute intervals, which means you can't really do a regular time domain analysis. So we actually had to, for this, convert over into frequency domain analysis. Then we have some of the more social science pieces that come with understanding some of the human dynamics. With a colleague and I, we are serving all of the Pittsburgh water customers, which is roughly 100,000 people, on what their understanding is of different stormwater events and willingness to pay for different solutions. There are some decision analysis pieces that come in as well. I know you guys have some classes on some of those and how you choose to create certain things based on what your utility functions are. We have some things like mental models, which help you understand where things connect and why, or they're also called expert influence diagrams. These can help you with your Bayesian probabilities and statistics. When you then apply these on there, you can run these through your systems to understand how people might be interacting with whatever mechanical device you're using. And finally, some of the pieces, since I am in the Department of Engineering and Public Policy, there's a good amount of work on public policy related things, such as something called deliberative democracy, where you bring folks together in a structured method to understand what their feelings and interests are in certain things. Now, before I move on, I'd like to, for each of these, describe who I've been working with on these projects. The first one to the left is myself and Neil Donahue, who is a tenured professor at CMU, and we have a first-year grad student working on that. The second one was myself and my former PhD advisor. This one was myself, 2 undergrads, and a PhD student, and the undergrad, I had her as first author on this paper. She did a great job. This one is myself and a colleague who were on the DOE funding for this. His name's Jay Ott. The surveys and interviews are myself and another research scientist at Carnegie Mellon. And these decision analysis, mental models, and deliberative democracy all involved a host of undergrads as well as masters and a few PhD students in creating them. So you can see for this, because I currently have a wide range of different projects, you're probably looking at it like, Kelly, this doesn't really make too much sense. You need to focus a little bit more. So indeed, that's what I've been working on doing in the future. Now, I work on urban adaptation for climate change and extreme weather events. And so I asked myself, what sector of, let's look at the US for this particular map, has the most greenhouse gas emissions? Maybe I'll focus on that one. Right? So this is a study from the EPA, and of course the electric sector is the one that has the most emissions, roughly about 31% for the fossil fuel emissions. And so what I'd like to focus on in the next 5 years here, or longer, I do think that it's longer than a 5-year program for this sort of stuff, but looking specifically at the urban adaptation for climate change and extreme weather events in the electric power sector. I'm not sure I'm going to get any single one of you to be able to repeat that later for me, so I'm working on shortening it a little bit as well. But looking at the electricity and some of the co-benefits of reduced emissions. So here are 3 studies that I currently have funding for, will transfer with me, possibly some of the grad students, wherever I go. And I'd like to tell you a little bit about them, and then about some of the things that I might see some synergies here with folks. So the first one was the smoothing of the photovoltaics in Gujarat, India. Now, for this piece, let me go get my water for a second, because I can already tell this is. Okay. So I'd like to pause for a second on this graph. This was one of the methods that we've used. It's called frequency domain analysis. So what frequency domain analysis does is it takes time data Instead of something that you're like, it's going to happen an hour, 2 hours from now, 3 hours from now, what you look at in a frequency domain analysis is it happened every hour or every 24 hours or things like that. So this is the generation of one power plant in Gujarat, India, in the frequency domain. And what you see are a couple things. You see a spike at a frequency corresponding to 24 and 12 hours, which is what one would expect for a solar photovoltaics when the sun's going up during the day, you know, roughly every 24/12 hours, something physically is happening there. And then you have some ringing that you would expect because of the Nyquist frequencies and such. And then it continues to have this slope going down. So what this means is that at high frequencies, which are things like every 20 minutes, every 15 minutes, there's a lot less variability or power in the spectrum than there are at these higher spikes here, which are at lower frequencies. So that slope is roughly about f to the minus 1.3. So when you add more plants together, here's 5 plants. What you see is you still see the spikes in the same spots, 24 and 12 hours. And what you start to see is that there's actually a steepening of this slope. So what does that mean? That means when you add 5 plants together, as opposed to just 1 plant, what's happening is that you're reducing the variability at the high frequencies. So you have a plant, maybe you have a plant here, a plant here, a plant here. You have a cloud passing over one, but not a cloud passing over the other one, so it sort of smooths out the fact that there's clouds passing overhead. This is really important for folks in the electric power sector, because this would suggest, hey, well, maybe if I just put a whole bunch of solar power plants together, I could smooth out all the variability of the clouds, and I could just rely 100% on solar power, right? Well, you know, when you start to go to 10 plants, you're starting to see some steepening of the slope as well, but it's not quite as much. And actually, when you start to get more towards 20 plants, or we added together as many as 30, you're seeing diminishing returns. You're actually seeing something that fits a theoretical limit that has been proposed of how much smoothing one can obtain through solar photovoltaics. And so we were the first ones to show this specifically with real-time generation data as opposed to theoretically or with other pieces. And we have this data set now for about 2.5 years. And what we'd like to do in the next couple years is continue on some of this work, both to see some of the plants we can't actually use because the data set isn't very good for one reason or another. But if you continue to collect data, eventually you'll be able to have enough good data that you'll be able to connect these things. Second is because we had such interest in this from the Indian government in Gujarat, India, we have several weather stations nearby that provide real-time weather data at 1-minute intervals that no one's really allowed to get unless you bribe the Indian government a lot. But because this is of interest to them, we're getting some of that data. And then you combine this with information about where resources are for solar power, for instance, water, or actually the solar influxes, combined with some interest from local folks in, do I want to have a solar cell, solar photovoltaic, or do I want to have something that is harvesting the heat at a different sort of frequency? It's called concentrated solar power or solar photothermal. Maybe we can put these in the same spot and co-locate them. There is also interest, of course, in co-locating solar and wind, because in some places wind only really blows at night, and the sun clearly shines during the day, so maybe you can smooth out some of the variability with that. And so there's a lot of different interesting things that one could do there. And I think that there's some folks here also doing some solar photovoltaic work that could understand a little bit of some of the constraints on and continue moving forward with. So the second one is this open decision support tool for greenhouse gas emissions. So this has on the x-axis the cumulative emissions mitigated, and on the y-axis the annualized cost. So basically what we've done to first order is take, what my PhD student has done, is take a bunch of different methods for building energy efficiency, so commercial buildings, residential buildings, whatever you have, different energy efficiency measures, and said, all right, well, if these are enacted, how much money could they save people, or will they actually end up costing money in the long run, versus how many emissions will they decrease? So let's take a look at what Zhishao has already done. So G-Shells, the first one was looking at a commercial building light bulb switch, taking actually these types of lights and switching them out with a slightly different type of light will actually give you the most bang for your buck. So if you're only going to do one thing in a commercial building, you basically switch out these, I don't know if it's like T10 to T20, but there's some specific things you could do. So it would save you a certain amount of emissions and it would also save you money. There are actually about 18 different options that G-Shells looked at that would save money over a 30-year return period. Okay? And they would all in total reduce emissions 10% below 2030, which is important for the local government because they've just come out with some policy statements on greenhouse gas reductions on what they will do in the future. And then of course there's a few that are really high up there. For instance, you really don't want to take your high emissivity roof. So if you have just a regular sort of roof and you put this like fancy schmancy material stuff on top, which is really awesome for reflecting light, it's actually still too expensive to really be getting you any return on your energy efficiency or other pieces. And so that ends up costing you money over the 30-year period. And of course, if you do sensitivity analysis on this on different years or whatever, you could see different things. So one of the things that I'd like to continue with here, the PhD student is now starting to pull in some air quality dimensions to this. So we have an X and Y axis, and he's making a Z axis. The real large difficulty with air quality in this sort of sense is that greenhouse gas emissions are global, well mixed. If you did something on your house and you did something on your house or apartment, I don't know, and you have a shack by the ocean, so sorry about that. But so it doesn't really matter where you put in your new clothes washer dryer. You're all going to have the same greenhouse gas effect on the environment. However, for air quality, it's a very, very local thing, right? You emit the air quality, or the air emissions, and it's right next to where they're emitted that a lot of the health damages happen. And this is a function of the fact that the air particulates usually stay in the atmosphere only a short time, on the order of days, maybe a week if you're really unlucky. And so these effects and these costs become very local. So the theoretical question here is, there's a lot of energy pieces that are being proposed in the future as having both greenhouse gas emissions and health benefits, but how do you really compare them together at the same time, since one is a global benefit and one is a local benefit? So he's going through with some chemistry folks. He's the first ever PhD student or second ever PhD student at Carnegie Mellon who's doing both engineering, public policy, and chemistry. So he's trying to figure out how to do that well to be able to provide some information to different electric folks on some of those issues. And of course with, and I'm still going to get the acronym wrong, but PA, Climate Health, Patch. I have a strong interest in, interacting with you guys in the future. Maybe this would be something that we could chat more about. The third piece is what was first the NOAA SARP proposal, Sectoral Applications Research Program proposal, successful, and then an NSF RIPS project, and it's looking at the resiliency in the energy and water sectors in the Tennessee River Valley Authority. The Tennessee River Valley is actually a really neat place to study. Aside from the fact that, Tennessee's awesome, you have things like the river, the watershed around it, so the place that drains all the water into the river, is almost exactly the same as the electric utility in the area and the boundaries of that. So it makes it a really easy case study to talk about some of these things. Plus, the Department of Energy has cited this as one of the places that in the future, power plants especially will have some problems. Many of the power plants there currently are once-through cooling power plants, which means they take a bunch of water, they cool down stuff, and then they spit it right back out into the river. And in the future, this area is actually expected to have, because of changes in precipitation and decreased mountain snowpack, actually less water available for the power plants. And so the power plants are going to start to be at risk and need to consider how to alter, maybe do some of the things that are done here or out in California for cooling, perhaps even dry cooling, that would be crazy, in these areas. So this is a multi-university, multi-million-dollar project. We have basically 4 parts to it. We have at the beginning and actually co-production knowledge throughout, this information on society. So I have a PhD student now who is working with one of the social scientists that I am working with on one of the earlier slides, and she is going out and doing very rigorous interviews with different experts in the field to see what different folks understand and how they interact with each other. And one might say, well, anyone can do an interview. Not exactly. There's actually a lot of difficulty to doing this correctly without injecting your opinion and getting the information that you need, not what they want to tell you. And so that's a lot of what's going on there. And we're seeing what are some of the actual energy, water, and operation restrictions that are happening on these in the future. Then my second PhD student is working in this area in, well, no, sorry, I lied. This is not my second PhD student. This is the, I don't know why I put water first. Anyway, so with the information from the co-production of knowledge, we have it leading into one side of the piece, which is the water supply and demand. So we're working with hydrologists at University of Washington to see what's happening both in the regular flows without people in the way, naturalized flows, and then if you add in some of the dams and other restrictions, what's happening with these and what might be the shortfalls in the future across a range of probabilistic scenarios. Then that's where my PhD student comes in, into the energy side. And here we have, again, the energy demand and supply, and some energy shortfall operations and restrictions. And the student is taking some of the information from the water demand and supply, as well as information from society, and then putting them into a very complex optimization model called Plexus, which optimizes how the demand and which, how do I say this simply, which power plants are turned on at what times over multiple years, given certain restrictions. And they have in it a lot of thermodynamics as how the plants operate, as well as information about water temperatures and releases, and some of those mechanics as well, including also some information about how electricity actually flows down transmission lines and others. And so he just went through qualifiers, and fingers crossed he'll probably come out of that okay. No, I'm kidding. He's fine. We're pretty sure he passed. I won't know officially until another week from now. But. And then so the next 2 or 3 years of pulling some of this information together and taking it back to the different professionals, seeing along the way they're giving us input at different workshops to see whether these information that we've collected, these data, might be useful. And so this is one of these energy water problems. And one of the things that's really great about here is you have this powerhouse that has a lot of energy stuff that's being introduced. You actually have at CSU a very good hydrology group, and you also have a lot of ag folks, as well as just here in mechanical engineering, some of the biofuels and other pieces. So I think that this could be something that would be of interest both to wrap up the project, as well as to move forward, bringing in some of the food, energy, water nexus components in the future. And then, this is all words. I know, I apologize for that. I couldn't come up with a pretty slide to do this. But what I went through is the 3 big things: the hazards, the society, and the interdependencies. I wrote out some questions that I thought might be starting discussion questions with different faculty here of things that we might be able to do in the future. And for instance, there's some hazards, electricity-related stuff. It's basically everyone across the board here. Maybe there's some optimization of places, I think with Kim perhaps. Maybe some of the social sciences of why aren't people adopting some of the hybrid vehicles or biofuels or some of the other advanced energy technologies with you. There's, of course, a bunch of environmental justice considerations, which seems to fit possibly with the postdoc, who I'm going to meet tomorrow, but now he's a research scientist and director of the institute. I think his advisor just left. Oh well. And then, of course, some of the bread and butter topics I just talked about are what are the effects of semi-electric use on the air pollution, climate, and the environment, and there's a couple folks here that work on that. There's also a lot of interesting tech that's happening in the mechanical engineering department, from some of the plasma stuff that different folks are doing, some of the aeroastro stuff, and of course those have very interesting interactions with the environment, and I think there could be some neat questions we could ask there. And then, of course, there's some interdependencies, and I just put Anthony here, but I would assume that would sort of go across the board as well. And again, these aren't things like, yes, of course, this is the exact question to answer, let's start about tomorrow. They're more like starting discussion questions. Because this is what I view as the Gantt chart, or what I'm going to be doing for the time here. I have these 3 projects, which will continue for some length of time. And then a couple of these different questions, hopefully more than just 2. The things that I would interact with different faculty, staff, students, and others here on some of these pieces in the future. And I expect that would probably take me out to about 5 years. But of course, this sort of work is not just something that's a 5-year program. It's something that's really, the problem of our next generation of how do we move into these places with dealing with our fossil fuel use and the effects on climate and the risk reduction that we're going to need to take to protect our cities. Currently, 50% of our people live in cities, and in a couple more years, it's supposed to be something like 80%. How do we supply them and protect them in the future? So there are a ton of different folks interested in this sort of work. These are all folks that I've had one-on-one discussions with about funding, and they are to different extents funding or collaborators. For instance, the U.S. Army Corps of Engineers has a resilience group that is very interested in risk reduction of different things. You have a lot of course, the emergency management with FEMA, DHS, and you also have a lot of different groups that maybe are more consulting, do various GIS group. I think there's a lot of good GIS here though. And of course, like NOAA and some of the others. So let's take a look real quick at some specific funding proposals because I was asked to suggest some of these that might work. So there are a few that I'd like to call out. The first one is the 2 big ones at NSF. The Food, Energy, Water Nexus is one big one that I think we here at CSU are poised to take the next step on and become leaders there, as well as some of the coupled human-natural systems, because we do have a wide range of good folks here that do some of those social science, economics type work, and I think there's a lot of interest in these. These are all multi-million dollars, but they also have smaller grants as well. But I think these could be 2 that would be really good to look at. Then of course NOAA, I just put 1 here because I was sort of running out of space, but they have a bunch of different things that are applications-based research, where they want folks to take climate change knowledge and apply it to mechanical engineering, or apply it to civil engineering in some way to see how these problems of tomorrow might get solved today. Another one, of course, are the DOD, EPA, DOE type pieces. I do already have funding from DOE. I should point out I have funding from NSF, NOAA, and DOE. That's for the 3 projects that will transfer. And you have things like CERTIP, you have things like energy and water, new technology. Some of you are probably funded by Minerva or some of the others. And I think that also for our mechanical engineering department, there could be some interesting proposals we could follow in this space. And because it's right down the street and I have a colleague there, you have the local folks as well, USDA, US Forest Service, the tribal folks, and